Wow, first, thank you for the great reaction from last night's video. So today, and I also like to thank the viewers who helped answer the questions that was posed. So today we talked about the zksnarks algorithm. I did a little research on it. It's quite a cryptographic algorithm there, and so as you'll see, it is a little bit of a challenge, but I found two articles here, and I'm trying to see what you can see. It looks like this window is too big. So I'm going to shrink it down, only because then I can put it on the screen properly. There. That's a lot better. Okay. So I found this article, and this is from media.consensus.net, which seems to have a lot of good stuff. This is a little bit more understandable than the other one that I found. Basically, when we talk about these are advanced cryptographic algorithm, the whole idea is for the verifier to be able to convince him or herself that the prover knows something secret, a secret parameter called a witness, satisfying something, but without telling it to them. So they talk about here you have a public input and the secret witness input. The output of the program is either true or false. Given a specific input, prove that the prover knows a secret input. So, the example they give here is, suppose Bob has a hash of some value, and he wishes to have proof that Alice knows the value S that hashes to H. Normally, Alice would prove this by giving S to Bob. Bob would compute the hash and check that it equals H. However, suppose Alice can't reveal that value. The example I read in another paper was, I forget what was that, where I'll have to look, I think it's in the other paper, where the hero has to prove that he knows how to open the stone door to the thieves, but he can't let them hear the secret word, so he makes them be far enough away that they can't hear it, but close enough that if he tries to run away, they can fire arrows at him. So this is the general idea. So Alice can't give Bob the value, but she wants to prove that she knows the value. So you can see it. The hash equals, it takes in a public hash and a secret value and returns true. Translate, okay, so here's a function that needs to create a proof that Alice needs to create a proof that she possesses as such that this function C with the hash value and her secret is true without having to reveal S. This is the problem that this zksnarks solves. And so this thing goes into the algorithm, a key generator. It takes a secret parameter and a program and generates two publicly available keys, a proving key and a verification key. So the keys are public parameters only need to be generated once for a given program. The prover takes the input, as input, the proving key, and a private witness, so it's a private value, And proof is a function of the public key. Let's see what X is here. Public key, witness, and what is X? An input, another public input, and a private witness. So the verifier computes with the two public keys, the two public pieces of value, and the proof that's generated by the prover, and it returns true if it's correct. So that's the whole idea. You have the person who's trying to prove that they know something generate the proof, and they provide it to the verifier that has essentially the same a public input, the verifier public key, the verification key, and the value, the public value X, and then the proof, and it's going to return. There's a secret parameter used in this parameter makes it tricky to use the zksnark in real world applications. Okay, so let's see. I'm trying to see if lambda, the parameter makes it, the reasons that, okay. Anyone who knows it could generate fakes. Yeah, so that's the issue. They use this lambda value. This is not the secret. The secret is the W, but they have to use this secret value to generate the two public values. And obviously the security risk is if you have, if input, and if you specifically any program C and public input X, given any person who knows lambda can generate a fake proof. So it has to be done in a very secure situation. And so, you know, it's it's kind of tricky. So developers started trying to incorporate it. The generators run off-chain to produce the proving key and the verification key. And then it can be run within a smart contract, which we saw in that example last night. And then, let's see, suppose we have a simple token contract, would have its core mapping. So you have an address to balances, but replace the balance with a hash of a balance. We're not going to hide the sender receiver, but we're going to hide the balances as confidential transactions. So two zksnarks would be used to send tokens from one account to the other, and two different proofs. You could see this can get kind of complicated. So under normal conditions, you probably would not need to use this. But if you have something confidential, and this, let's see, the main idea is that the sender will use their starting balance and the transaction value as private inputs, and hashes the starting balance, ending balance, and value as public inputs. The receiver will use the starting balance and the value as secret inputs, and hashes the starting balance, ending balance as public inputs. So it's not. So here's the sender function, sender balance before. So hash, and we have a, so X represents the public input, W represents the private input, and you can see it does a SHA of W, and so on. It's using a bunch of hashes here. And the receiver will also take the same inputs, and you know, so let's see. Now this is an example of doing the zksnarks verify. So in order to do this, the only updates to the blockchain are the hashes. So you never put the actual values on the chain, but they are handled off-chain. So this is a concrete example. How much would you have to do this? Again, these are for, in my view, for special transactions. I can see, you know, there might be some applications where you really have to hide that data. Perhaps also maybe use it in some kind of privacy coin. Although it doesn't hash the sender or receiver, so that may be an issue. So this is a pretty good article here. Goes through why you would use it. I guess if you actually want to, if we incorporate it. So this is interesting. They talked about the fact that there was a celebration when they actually ran it. I don't know if it's this article or the other one. Let me show you the other one. The other one gets into some real heavy math involving matrices and so on, and talks about the history of zero proof algorithms. But this is where they give that, let's see if they talk. Yeah, this is the Alibaba and the 40 Thieves. So in order to save his life, he needed to prove the robbers that he had a password, while at the same time couldn't tell them the password. So the robbers gave him enough space they couldn't hear the password, but close enough that they could fire an arrow if he tried to escape. And he was able to demonstrate opening and closing the door. So that's, again, a zero knowledge proof. They couldn't know the password, but they had to verify that he did have the password and could get into it. So this article here goes into a great deal of detail on how it works mathematically. I think as a practical matter, unless you're into cryptography, you're probably going to find a cryptographic algorithm, just like like pretty much any modern language has some library that does, you know, the SHA hashing and things of that nature. So, the second thing I want to show you just before we end, real quick, since there were some questions on the heavy, light, and so on, heavy, light, and full power. Let me move this up here. Let's see. I think there we go. Let's move. So this is my Theta Edge worker, and if you go in here and you look at power mode, this is where you would change it. And why you're not seeing it, I don't know. But under Edge Compute, if you click on Edge Compute, you'll see power mode, and you can change it to light, medium, or full, depending on your use of the computer, your power of the computer. You know, you may want to have it on full during the day to earn, because it's a trade-off. First, let me mention it's a trade-off. The higher the level, obviously you'll earn T-fuel faster, but it's going to use more resources on your computer. You may not care if you're at work all day or you're sleeping. You don't care. You just want to, fine, go ahead and earn me T-fuel as quickly as you can. If it's something that, let's say you're working from home and you got to balance this node with doing the stuff you have to do for work, or you want to play a game, or whatever the case may be. Like I have out of the park baseball perfect team running in the background, so I can see how my team's doing. What can I say? Fantasy sports on steroids. But anyway, so that's how you can change the mode, and it's really going to depend on your situation. It would be interesting. It's unfortunate that it's only Mac and Windows. I'd love to see them get a Linux version, because then you can put one of these, maybe you could even get one of these puppies on one of these, you know, little one board machines, the Nano, or the, you know, a Raspberry Pi or something of that nature. That would be cool. But unfortunately, is not yet a Linux available. So anyway, hopefully this has been helpful. And again, I want to thank you all for your reaction to the last video and for the viewers who helped answer questions. And if you enjoyed this, if you found it helpful, then please give a like, and please subscribe and ring the bell so you get notified of further videos. And I will speak to you next time. And don't forget, feel free to ask questions. So speak to you next time. Take care.